So we're going to practice using our two methods for calculating values with the CAPM model. In both of our example problems, we're going to use, or in both cases, we're going to use the same example problem. A boy is sledding down a hill, and the boy accelerates at 1.5 meters per second squared. We're saying he starts from rest, and we want to know in what distance he would reach a speed of 7 meters per second. The first method we're going to look at is using graphs. So as mentioned, we need to draw a velocity versus time graph. And there's some important pieces of information that I see in this problem that'll help us draw this graph. First of all, it gives me the fact that he started from rest. That tells me that my initial point on my axis is going to be 0. Second, it says that we're looking for at what distance he reached a speed of 7 meters per second. So we're going to stop drawing our graph once we reach 7 meters per second. That helps me know how high I should make my horizontal axis. So I'm going to go 1, 2, 3, 4, 5, 6, 7. I don't need to go above that because I'm going to stop drawing when I get that speed. We'll go ahead and label that axis, as you should always do, with the word velocity and our units, which are meters per second in this case. Another piece of information that's going to be really important to us is the acceleration, 1.5 meters per second squared. That tells me that for every second, the velocity increases by 1.5 meters per second. So that's going to give me a little bit of an idea of what I can do for my time axis. So after 1 second, the speed will be 1.5 meters per second. After 2 seconds, it would be 3 meters per second. After 3 seconds, it would be 4.5 meters per second, and so on and so forth. So I'm going to go ahead and label my axis as 1, 2, 3, 4, 5, 6, 7, 8. Now that'll probably be more than I actually need, but that's not a big deal if we go a little bit higher than we need. And this is, of course, time measured in seconds. So let's go ahead and actually draw our graph now. So I mentioned already that we're going to use this acceleration to help us figure out what the velocities are. Remember that acceleration is the slope of a velocity versus time graph. So as I mentioned, after 1 second, we'll be traveling 1.5 meters per second. After 2 seconds, it would be traveling 3 meters per second. Notice I'm just adding 1.5 for each second. At 3 seconds, it would be going 4.5. At 4 seconds, it would be going 6. And at 5 seconds, it would be going 7.5. Okay, so if I draw my line here, it goes something like that. Now, I want to know some information about when it reaches a speed of 7 meters per second. So I'm just going to draw in a little guideline for myself here. Straight across, 7 meters per second, and then straight down. Now this isn't going to be perfect because I'm not using graph paper here, and that's okay. I'm not looking for exact perfection. Now, it says at what distance would he reach that speed? Now, when we're moving in a straight line, distance is the same thing as displacement. And we learned that displacement is the area between a graph and the horizontal axis. In other words, what I'm looking for here is the area of this region that I'm shading in right now. It's a triangle. So we know that area can be found by doing 1/2 base times height. In this case, my base is approximately, I'm going to say about 4.75 seconds. It's not going to be perfect because, again, I'm not using graph paper, and I'm okay with it not being perfect. And then the height we know for sure is 7 meters per second. When I multiply this out in my calculator, I get 16.6. And notice if I were to multiply those units out, I'd get meters. there's the answer to my question. He goes 16.6 meters when he reaches that speed of 7 meters per second. So this was an example of using method 1, how to use graphs to calculate our unknown value. And it makes sense to go 16.6 meters as he's going downhill. Let's move on and look at the second method, which involves using equations. This should say method 2 at the top. So same problem, but this time instead of drawing a graph, we're going to use one of those 4 equations that we learned earlier on. So let's start out, we're going to use that gummies method I talked about in class, which means I'm going to start out writing out what my knowns are. So the first number I see is 1.5 meters per second squared. That's I'm going to say A equals 1.50 meters per second squared. And then I also see that 7 meters per second. Now, we know that the velocity, whether that's initial or final. And to decide that, you just want to think about your problem. Is that the speed or the velocity that he's starting out with? Or is that the speed or velocity that he's kind of finishing with? Well, the problem says he started from rest. So he's not starting at 7 meters per second. Instead, he's starting at 0 meters per second, which tells me that this must be a final velocity. Those are the 3 things that are given to us. Those are our 3 knowns. And that means I'm going to move on to the U step of the gummies method, which is figuring out what's my unknown. So for my unknown, we look at what the problem's asking us for. And in this case, it says, in what distance would he reach a speed of 7 meters per second? So distance is my unknown here. And in this case, rather than writing down B equals question mark, I'm going to write down delta X equals question mark. Because I care more about the displacement, because again, because he's moving in a straight line, the distance and the displacement are the same thing. Okay, now we know this thing's accelerating. It doesn't have a constant speed. So we know we're talking about the CAPM model. And that means I'm using one of those 4 equations. So take a look at those 4 equations. You should have them written down somewhere. Notice that in all of my things that are written down, I don't have time written anywhere. That means my best option is to pick an equation that doesn't include time. And the equation that doesn't have time anywhere in it is the equation that says V final squared equals V initial squared plus 2A delta X. Okay, so this is my equation, and delta X is the thing I'm looking for. So I can plug numbers in. 7 meters per second, and then I have to square it. Don't forget about squaring that. That's really important. That's equal to 0 because V initial is 0 plus 2 times my acceleration of 1.5 meters per second squared times delta X, or the thing I'm looking for. We know that 7 squared is equal to 49, and I would square the units as well, so meters squared per second squared. And 2 times 1.5 is 3. Units stay the same as meters per second squared. So then to solve for my displacement, I would divide both sides by this 3 meters per second squared. When I do that, I find that delta X is equal to 16.3 meters. Again, a reasonable number. And if we were to look back at the previous method, the previous slide here, we see that the 2 numbers, the 2 values we got are really close. Sure, they're slightly different, but that's only because I didn't draw my graph on graph paper. So I didn't have a perfect value for when the speed was equal to, I did perfect time value for when the speed was equal to 7 meters per second. And that's totally fine. As long as you show your work and you have something that's reasonable, I'm happy with your answer. So again, we'll do more practice with both of these methods. And in general, it's okay for you to choose one method over the other, whichever you prefer.